Okay, hello everyone, welcome back to another video. I've been ill for the past few weeks, but I'm back today and we're coming back with a great problem. It's the sum from n equals 1 to infinity of x to the n times gamma of x, all over gamma of x plus n plus 1. Now whenever I see the gamma function in a relationship like this, where we've got a gamma x on the top and a gamma x plus something on the bottom, I'm instantly kind of reminded of the beta function identity, that beta of xy is equal to gamma of x times gamma of y over gamma of x plus y. Now of course we've got our x here and we've actually got an n here, but what we would want to have on the top next to our gamma of x of course would be a gamma of n plus 1, because if we had this here then this whole part would just be beta of x n plus 1. And how can we manipulate what we've got in order to bring that factor into the numerator? Well, we've just got to remember that n times gamma of n is gamma of n plus 1. So if I were to multiply my numerator by gamma of n, then I would end up with this n multiplied by gamma of n, giving me gamma of n plus 1, and I'd have the beta function relation that I want. And all I have to do, of course, is just divide by gamma of n at the same time so that the value of the sum doesn't change. So I can equate this to the sum from n equals 1 to infinity of x to the n divided by gamma of n, because of course I want to cancel out what I'm doing, times n times gamma of x over gamma of x plus n plus 1. And of course, as we've already said, n times gamma of n is gamma n plus 1. And here we have got the beta function evaluated at x and n plus 1. Now we're also going to use a second beta function identity. It's that beta of x and y is the integral from 0 to 1 of t to the x minus 1 multiplied by 1 minus t to the y minus 1 with respect to t. And so that means that this beta of x n plus 1 we can rewrite as an integral, leaving us with x to the n over gamma of n multiplied by the integral from 0 to 1 of t to the x minus 1 times 1 minus t to the n, all with respect to t. Now I'm going to create some space up here to continue with our problem, but I'm not going to go into the rigorous proof of why we're allowed to do this today, because it's not the focus of the video, but using the convergence of the integrals and a bit of Fubini's theorem, we can verify that the summation and the integral are interchangeable. And that means that we can rewrite this as an integral of a sum rather than the sum of an integral. Now I'm going to have all of my terms that don't involve n outside of the sum, and the only one I've got is t to the x minus 1, and I'm going to have all my terms that do involve n after my summation. So that's going to be x to the n multiplied by 1 minus t to the n all over gamma of n with respect to t. Now of course, because the gamma function here, gamma of n, is within a summation and the summation is only taking positive integers, we can say that gamma of n is just n minus 1 factorial, which is of course what it's defined as. And so what we're looking at here is actually very close to an exponential Maclaurin series. Right, we've got a factorial on the bottom and we've got a numerator to the power of n. But the problem is that our power doesn't match our factorial. So we know that e to the x is the sum from 0 to infinity of x to the n over n factorial. But our power is n and our factorial is n. Here our factorial is n minus 1 and our power is n. Now given that we're starting from 1, I want my power to be n minus 1 and my factorial to be n minus 1. And so I'm going to take out a factor of x and a factor of 1 minus t in order to reduce their power in my summation. So that's going to leave me with t to the x minus 1 multiplied by 1 minus t multiplied by x, all times the sum from n equals 1 to infinity of x times 1 minus t to the power of n minus 1, all divided by n minus 1 factorial with respect to t. Now clearly this we can rewrite as in terms of an exponential, and that exponential is e to the power of x multiplied by 1 minus t. Now this integral we're left with here, it can look like something that's going to be very tedious. But I think the best way to approach it is just to consider the integrand and think, what could we differentiate to end up with an integrand like this? And I think actually it will be helpful to expand out our brackets. So first we're going to end up with x t to the x minus 1 e to the power of x times 1 minus t. And then we're going to end up with minus t to the x times x e to the x times 1 minus t. And I think writing it out is so important for this question because this makes it clear that our integrand is simply the result of using product rule on a function. And this function is, and I'll convince you of this in a second, t to the x multiplied by e to the x times 1 minus t. And of course this becomes quite obvious when we look at each term. So here we've got x times t to the x minus 1. Now that's clearly what happens when we take the derivative of t to the x, and then we've kept our exponential term the same. And of course that's what we do with product rule. We differentiate, keep the same, plus the same, and differentiate. So what we'd expect to do over here is to keep our t to the x the same and multiply that by the derivative of e to the x times 1 minus t, which does end up being negative x e to the x times 1 minus t. And so this clearly here is just the derivative with respect to t of the following function, and so that implies that our integral must be equal to this original function, t to the x times e to the x all times 1 minus t, evaluated between the bounds that we have, and that is of course 1 and 0. Now when t equals 1, we've got 1 to the x, which is 1, and e to the x times 1 minus 1, which is 0, of course leaving us just with 1. And when t equals 0, our lower bound is 0. And that means that our integral is equal to 1, and therefore our sum is equal to 1. So just to tidy things up, the sum from n equals 1 to infinity then of x to the n times gamma of x divided by gamma of x plus n plus 1 must be equal to 1. I hope you guys have enjoyed this video. Sorry for not uploading so much recently, but I will be back onto it now that I'm getting better. And I'll see you in the next video. Let me know if you have any suggestions, and thanks for watching. Bye.